So all of you listen here. So we are talking about wave optics, chapter 10, NCERT book, wave optics, class 12. Okay. So you see topics to be completed. First, Huygens principle. Next, using Huygens principle, prove the laws of reflection and refraction. So first we'll see about refraction, after that reflection, then interference, then YDSC and Young's double slit experiment. Okay, that YDSC basically Young's double slit experiment, and a single slit diffraction. Also we'll see. Okay, so all of you see first what about Huygens principle. Already you know, I have discussed already. Okay, so what Huygens principle basically says here, now light travels in all directions in the form of waves. That is what the main point. So according to Huygens principle, each point on the wavefront acts like a source of secondary disturbance, and wave emanating from it travels in all directions with the speed of wave. Yes or no? So the speed of wave equal to speed of wavefront, and that each point on the wavefront act like a secondary disturbance, and from here whatever wavefronts are emanating, that waves are called basically secondary wavelets. That wavefronts are called basically what? Wavelets are called secondary wavelets. Okay, that means suppose this is the point source. For point source you have a spherical wavefront. Each point on the spherical wavefront will act like a secondary source. So one point you take here also, will act like secondary source. Take a point here also, act like secondary wavelets. Okay. So whatever I have drawn now, this one is secondary wavelets, and this is suppose point source. In the middle it is a point source. So these are basically what? These are basically wavefronts. The circles, big circles, whatever I have done, they are basically concentric spheres. So for point source, what is the wavefront? Point source, what is the wavefront? Spherical wavefront. So remember, for point source, what type of wavefront forms? What type of wavefronts? Spherical wavefront. Similarly, for a line source, what type of wavefront? Line source, cylindrical wavefront. So remember, for line source, if I will do line source, for that one you will have cylindrical wavefront. Okay, and if I do one parallel light rays, okay, so here I will do here. So check here, if I will do for parallel light rays, then this type of plane wavefront will form. So this is the parallel light rays are going here, and all will be perpendicular here. So remember, for parallel rays of light, or parallel beam, okay, shape of wavefront is what basically? Now parallel planes or plane wavefront, you can tell, parallel planes. Okay, and always remember, the direction of propagation of the ray or wave is perpendicular to always wavefront. Wavefront. So here it is plane wavefront. So always perpendicular, 90 degree. Either it is a point source, line source, or parallel rays of light. Always remember, wavefront is always perpendicular to what? Light ray. Okay, light ray. So this idea also remember. And suppose some plane wavefronts are passing through a prism. Plane wavefronts are passing through the prism. Suppose they are coming like this. Okay, after refraction, they will just tilt and it will go like this one. So this is your plane wavefront, refracted wavefront after prism. So this is the prism is there. It will go like this. Suppose I have a point source at a focus of a convex lens. Remember, at a focus of a convex lens. So that means I will have a spherical wavefront. Now here, if light rays will go, then image will form at infinity. I will have plane wavefront here. So here what wavefront? Plane wavefront. Here plane wavefront. Okay, plane wavefront. And here you have spherical wavefront. Spherical wavefront. Spherical wavefront. So this is your object actually. This is your object and this is your image. Your image at infinity. Image at basically infinity, and if light ray going to very large distance or coming from large distance, that will be plane wavefront. So this diagram they will ask you to draw. Hello, Inia, try to understand. Whenever a object is there at focus of the convex lens, then image will be at infinity and image wavefront will be, this is the image wavefront. So image wavefront will be plane wavefront. Yes or no? Similar way, if parallel rays are coming for a convex lens, okay, so our object at infinity, parallel rays are coming for a convex lens, then after refraction, I'll have spherical wavefront. What wavefront I'll have? Spherical wavefront. Okay, like this I'll have spherical wavefront. So listen here, this is my plane wavefront, this is my object at infinity, plane wavefront, plane wavefront. So now here I am getting what? Spherical wavefront, spherical wavefront. So this spherical wavefront is basically refracted wavefront. For this case it is refracted wavefront. And what is the radius? The radius of the sphere, radius of the sphere will be how much? Now focal length of the lens. Okay, radius of spherical wavefront, radius of spherical wavefront is basically focal length of this lens, focal length of lens. Remember this, focal length of lens. Okay, because here light is coming like this, light is converging actually, and this spherical also you can call basically converging spherical. What you can call? Converging spherical wavefront. That also you can say. Okay, so converging spherical wavefront. Now, if light ray is coming to a concave lens, a plane wavefront coming for a concave lens, okay, that means object at infinity, and after reflection, what will happen? After reflection, it will meet at focus. So this is the light ray. This is the light ray I am drawing. Yellow color pen I am doing everything. Listen here. So this is the plane wavefront. Now plane wavefront becomes what? Plane wavefront becomes spherical. Plane wavefront becomes spherical wavefront. So you can write here. So this is your spherical wavefront, and its radius also spherical wavefront. And the spherical wavefront, if radius I'll talk, radius will be equal to, okay, f focal length of the mirror, or basically radius of curvature by 2. Okay, r is radius of curvature, f is focal length of mirror. Okay, focal length of mirror. Okay, and r is radius of curvature of mirror. R is radius of curvature of mirror. So this is the idea to remember. This all diagrams they may ask you in exam to draw. Okay, hey Darshan, listen. This all diagram they may ask. Either plane wavefront is coming and passing through prism. What is the refracted wavefront? Now if this is plane wavefront, I am writing shortcut WF wavefront, then this will be also plane wavefront. This will be also plane wavefront. And here if a plane wavefront is coming after refraction through the convex lens, then what it will become? That will become spherical. It will become spherical. Yes or no? Now next. And if a spherical wavefront is there in object, okay, this is your object here. Here it is object is plane wavefront. Your image, this is your image. Image at focus. So here if object at focus, then what is happening? Object at focus, then image will be at infinity, then plane wavefront. So here spherical wavefront will become plane wavefront. Yes or no? All this ray diagram they may ask, or diagrams they may ask to draw. Okay, plane wavefront, spherical wavefront. So here I have done dotted line. I have done the spherical wavefront for concave mirror. Okay. So radius of the wavefront is nothing but it is r by 2. Radius of curvature by 2. Okay. So this much idea you must remember. Now next listen. Using Huygens principle, one question listen here. Using Huygens principle, prove that laws of refraction. Okay, so laws of refraction basically two laws you know. Okay, one is about incident ray, refracted ray, all will lie in one plane, normal, all will lie in one plane, and a second one is basically Snell's law. Okay, n1 sin I equal to n2 sin R. So here what you do, now when wave travels from rarer medium to denser medium, rarer medium, listen all of you, when the wave travels from rarer medium to denser medium, then what happens, this is your rarer medium, this is your denser medium here down. Okay, in a box it is given basically, this box is basically a denser medium. Okay, refractive index of denser medium is given n2, n2 is given, here refractive index is given n1 for rarer medium. Okay, now next listen. So when light ray is coming, light ray, two light rays coming here, right, you see here light ray is coming here, white color it is given basically. So light ray is coming here, two light ray, now you do a perpendicular like this. Now this is your incident wave front, and another perpendicular draw like this, that is a refracted wave front, because this is a refracted ray, yes or no? So now listen all of you. So here what is happening, now here you have to put that, you have to prove that n1 sin A equal to n2 sin R. How to prove? Now first you consider here, your two triangles are coming, your ABC points you give, ABC points. Now from triangle ABC, what I can get? Now BC is B1 tau, BC is B1 tau, BC, V1 tau. Now sin I, if I want to find sin I here, then it is V1 tau by SC. You can check the triangle, and this angle is 90 degree. So B angle is 90 degree, so it will be sin I equal to V1 tau by SC, and from the triangle AEC, I can get what? Sin R equal to V2 tau by SC, and if equation 1 by equation 2 I will do, I will get sin I by sin R, which is V1 by V2, and V1 value you know, C by N1, V2 value C by N2, if I substitute, I will get this is N2 by N1, so which is nothing but N1 sin I equal to N2 sin R, yes or no? So in this way, you are getting your Snell's law. Okay, so this one condition, remember, rarer to denser medium. If question they asked, what happens if light ray or wave is coming from denser to rarer, then picture will be changed only, other things will remain same, derivation, and here remember, here n1 will become greater than n2, previous case n2 was greater, okay, and v1 will become less than v2, but previous case v2 was less than v1, okay. This is the difference happening. So here rarer medium is there, here denser medium is there. Now here light ray is coming and passing like this. So this is your incident wave front, you can tell this one. This is your incident wave front now, in a denser medium, incident wave front, and this is your refracted wave front. And while taking this diagram or condition on I is what? Now I is basically less than IC, so that refraction is happening, where IC is critical angle. IC is basically critical angle. So we consider this and we took here I less than IC, then only refraction angle R can come. Yes or no? So here also same derivation. To consider triangle ABC and AEC. Sin I, sin R you find sin I and sin R. Then equation 2 by equation 1. Equation 1 by 2 you do basically. Equation 1 by equation 2. Equation 1 by 2 you do. You will get sin I by sin R equal to same way. Okay. Sin I by sin R equal to same way you will get. Yes or no? V1 by V2. After getting V1 by V2, you substitute V1 equal to C by N1, V2 equal to C by N2. You will get N1 sin I equal to N2 sin R. Yes or no? Is it clear? Okay. Now next listen. Next is using Huygens principle prove that laws of reflection. So all of you listen here. Similar way, you take a reflecting surface and take two parallel beam of light. So here, now take a perpendicular here. This will give you basically incident wave front, and here light will reflect also. Now from that you take a perpendicular. This will give you reflected wave front. This is the incident wave front. This is the reflected wave front. Now here also same thing. A, B, C and AEC triangle you consider. Two triangles will come which is shown in the picture actually. Okay, one is ABC. You can consider here ABC triangle. This is the ABC triangle. Another is AEC triangle. Another is AEC triangle. Okay, so both the triangles if you will compare, what you will get? Now you will get what? Now AC is basically common base. AC is basically what? Common base. So AC will be basically your common base. Okay, you will consider triangle ABC and triangle AEC. So AC is nothing but it is common base. Common base, and AE, BC are equal. That is nothing but B tau. Okay, and AEC and ABC triangle are having equal angle. Okay, that E angle, B angle, which is 90 degree. So from this following data, what we can conclude? Now triangle ABC, triangle AEC are congruent. Then angle of incidence equal to angle of reflection. So this I and R will be equal. You can substitute that. And remember, the incident ray, reflected ray, normal at the point of incidence all lie in the same plane. So that is your law of reflection or laws of reflection you are getting. Okay. So basically I equal to R you have to prove here. So picture is given, then two triangles you consider, then you prove this. Okay. Okay. So now next is what? Next is about interference. Already you know interference is nothing but is a phenomenon of redistribution of energy on account of superposition of two waves. Okay, and if I consider two waves, one is I1 A cos omega t and another is Y2 A cos omega t plus phi, the resultant displacement is given by how much? Y equal to Y1 plus Y2. Then I will substitute the values, and if I will take here A common, then I will get cos omega t plus phi. So how it is coming? It is coming like cos A plus cos B, like that it is coming. And if you use the formula, it is 2 cos A minus B by 2 plus cos into cos A plus B by 2. Like this you can substitute and you can get. Okay. So this is your cos A plus B, cos A plus cos B formula. Cos A plus cos B formula is what? 2 into cos A minus B by 2 into cos A plus B by 2. If you substitute that formula, what I will get here? I will get resultant displacement is equal to Y equal to how much? 2A. Okay, 2A cos phi by 2. This bracketed term 2A cos phi by 2 is called as amplitude, and resultant intensity nothing but amplitude square. So resultant intensity is coming as this much. I equal to 4 I naught cos square phi by 2. So in exam they will ask the question, listen, Y1 equal to A cos omega t, Y2 equal to A cos omega t plus phi, then you find what is the intensity. So intensity this one. Okay, to try to understand this. Now next listen, your phase difference, phi is called basically phase difference. So phase difference is 2 pi by lambda into delta x, and delta x is called basically path difference. Okay, so if path difference is given, you can come to phase difference. After that you can come to intensity. Okay, now next listen, constructive interference. When phase difference is 2 and pi, where n is running from 0 to plus 1 plus minus 1 plus minus 2, then if you use phi formula as path difference, then path difference is coming L lambda, and phase difference is nothing but for constructive interference it is 0 plus minus 2 pi, all even numbers. Okay, integers, even integers including 0. Now delta x equal to similar way coming 0 plus minus lambda and all. Now remember, if two waves are having same phase or integral multiple of phase, even number, same phase or integral even number of phase, then only they will constructively interfere. You'll get a resultant wave like this, whatever given here. Okay. So now come to destructive interference. What are the conditions? Now phi equal to 2n minus 1 pi by 2 and phi equal to n minus 1. If 2 I'll divide here, I'll get n minus half pi, and here if phi formula I'll use 2 pi by lambda into delta x, I'll get about delta x. Okay. So here also you put n equal to 1, 2, 3 like that, and you will get phase difference and path difference formula or conditions. And here both are opposite phase. You see here both the waves. If one wave is in upward direction, another is downward, like that it is coming. So these are opposite phase. So opposite phase means destructive interference. So no interference is coming here, dark coming actually. Okay, no light is coming, no bright spot is coming, dark spot is coming. And together this constructive destructive interference happens in interference. Okay, constructive and destructive both the things happens in interference. That's why you get, for constructive you get bright fringe, for destructive what fringe? Dark fringe. So that much idea you keep in mind. And next listen. Suppose your y equal to a1 sin omega t and a2 sin omega t plus phi, or any other function, sinusoidal function, the resultant amplitude is this formula: a equal to a1 square plus a2 square plus 2a1 a2 cos phi root under, and resultant intensity is nothing but I1 plus I2 2 root I1 root I2 cos phi. This is the resultant intensity. Okay, and here you can take a max, a minimum value when phi is 0, that time a max equal to a1 plus a2, and when a minimum, when phi equal to 180 degree, that time it is a1 minus a2. Similarly for intensity also you can take intensity maximum root I1 plus root I2 whole square, and intensity minimum is root I1 minus root I2 whole square. And if I want to find what is I max by I mean, then I max by I mean is nothing but root under I1 I2 plus 1 whole square divided by root under I1 minus I2 minus 1 whole square, or you can remember this formula. Whatever formula is given here, that formula I have taken here actually. You can understand that also. And always remember I1 by I2, intensity is directly proportional to amplitude square. So this is the definition of intensity, okay, in terms of wave picture of light. Okay, amplitude square, intensity is amplitude square. So I1 by I2 is A1 square by A2 square. A1, A2 are up to amplitudes whatever given waves. And I1, I2 also you can take as W1 by W2, which are width of the slits. Okay. And I max minus I minimum if you will calculate, divided by I max plus I minimum I'll do, then I'll get fringe visibility. So this formula you remember. Okay. This formula you remember. Now next come. Now next listen, Young's double slit experiment or YDSC experiment. In this case you have two slits, one is S1, another is S2, which is coming from a primary source S. Okay, S source is there here, and rays are going here and meeting at point P, okay, from the slit, and delta x is basically path difference. Delta x is basically path difference, and from this configuration, if I calculate what is my delta x will come out to be d sin theta. Delta x will come out to be d sin theta. And delta x I'll call as path difference between the two waves. If there is a path difference, then there will some phase difference will come. Then only interference will happen and constructive destructive bright or dark fringes will see. So now all of you listen, for bright fringe or constructive interference. Okay, your delta x condition is n lambda. Delta x equal to n lambda, and delta x is nothing but d sin theta. So d sin theta equal to what basically it is? N lambda. Now next is sin theta can be taken as theta. Sin theta can be taken as theta if theta is very small. Now instead of sin theta, here I am writing theta, and theta is nothing but n lambda by small d. This is called angular position of nth bright fringe. Angular position of nth bright fringe. And theta value, if you check in picture, it will come y by d. y by d. So here you can check the picture. Theta value will come y by d. D the distance between slits and the screen. So now if I'll substitute that, I'll get y nth position for nth bright, which is nothing but n lambda capital D by small d. And if I'll consider n equal to 1, that is first bright fringe. So theta 1 is lambda by small d and y1 equal to lambda d by small d. Small d is basically distance between slits, two slits. Okay. So everything understand carefully. Similarly, second bright also you can find. Okay. Both angular position and linear position. Both angular position and linear position you check. Are you able to understand? No reach? Yes or no? Now next listen. For dark fringe or destructive fringes, destructive interference. Okay, your path reference equal to n minus half lambda and delta x equal to n minus half lambda. And delta x is nothing but d sin theta, already you know, that is n minus half lambda. The sin theta will become theta, you know, when theta is very small. Theta is small. Sin theta is nearly equal to theta. Sin theta is nearly equal to theta. Now next, if theta nth I want to find, then n minus half lambda by small d I will do, which is angular position of nth dark. Angular position of nth dark. Okay, nth dark. And angular position of nth dark, after that, theta equal to yn by d, you can substitute this formula and you can get yn, which is linear position of nth dark, n minus half lambda capital D by small d. N1 equal to first dark fringe, n equal to 2, that is second dark fringe. What formula coming, try to understand and remember your little different formula. Y1 you can give your y prime also for dark Norwich. Theta also theta prime you can give. Okay, because for bright you are using theta 1. So for dark you can give theta 1 prime as your wish. Okay. So now this is your dark or destructive interference. Clear idea? Now next listen. Next is fringe width. What is fringe width? Who can define fringe width? The distance between two consecutive bright or dark fringes. Okay, is called basically fringe width. Dark fringes is called basically fringe width, and formula is beta equal to lambda d by d. So remember, okay, fringe width is nothing but it is directly proportional to lambda wavelength. Lambda means wavelength. Okay, and d is basically what? Distance between slit and screen, and small d is distance between the slits. So remember, many things they will ask you here. See, angular separation does not depend on capital D, but angular fringe width depends on capital D. Sorry, that also does not depend. Angular means does not depend. Linear only depends. Linear only depends, or normally fringe width depends on D. Okay, but angular separation does not depend on fringe. That does not depend on capital D. Does not depend on capital. If you want to prove beta equal to lambda d by d, beta equal to lambda d by d, if you want to prove that, so take for bright fringe y2 equal to 2 lambda d by d. Here y1 equal to this much. Now subtract them. Y2 minus y1. Two consecutive na. Y2 y1 are consecutive. For dark also you check, same thing coming. So lambda d by d. This is a question in exam. You prove that fringe width is same. Fringe width is same for dark also, bright also. Dark also, bright also. Okay. And beta in a medium. Suppose you are taking any medium you are taking and you are immersing this YDSC experiment. Then refractive index is mu of that medium. Then beta medium equal to beta air by refractive index. Okay. So this idea should be clear in your brain. Yes or no? So about beta you remember this much. Beta is called fringe width. Beta is called fringe width. Okay, next listen. If you want to do intensity distribution in YDSC, what is intensity distribution in YDSC? The intensity versus path difference graph. Y-axis take intensity, here path difference. All of you listen carefully. This picture should do correctly. All are having same intensity. This your I max is given. And what is the intensity in YDSC. Now this is your 4 I naught cos square pi by 2. So this is the intensity formula for YDSC. You can write in general. Now listen, here all are same amplitude. So perfectly do for this one YDSC. This is the intensity graph. Okay. Now next listen. Diffraction. What is diffraction? Now the phenomenon in which light rays bend around the edges of an obstacle and enter to the shadow region is called diffraction. That means light rays coming here. Now I have one obstacle here. This is the obstacle is there. Obstacle. Okay. Now in the screen, in this region I should get shadow. I should get shadow region. But here I'll see. So bright and dark fringes are there. Bright and dark fringes, alternate bright and dark fringes are there. Okay. Now next lesson. So here this is the obstacle. Actually it's the shadow region. In shadow region you have alternate dark and bright fringe. So that is what the phenomena is called diffraction, because light ray from this edge of the obstacle it is bending here. It is bending and coming here. That is the region we are getting bright and dark fringes here. Okay, Mukundan, try to understand. Now next is what? Single slit diffraction. If I am considering a single slit here, okay, width is A. Now the diagram will, the experimental setup will be like this. Okay. Now where A is basically width of the slit and D the distance between slit and screen. So for nth minima, in this case nth minima means dark condition, your in theta n equal to L lambda by A, and if you multiply D it will become linear position, and central maxima. See, listen here, central maxima is little bigger size in diffraction. So here the formula is basically angular width 2 lambda by A and linear width 2 lambda by A into capital D. Now here lambda by A is the distance from the center to first minima. So here downward also same first minima. So that's why this is the region it is becoming lambda by A into lambda by A plus lambda by A, which is 2 lambda by A. Yes or no? So that is the region width of central maxima is 2 lambda by A. Okay, down also below also, this is the width. So this is basically first minima to first minima is width of the central maxima. Okay, so this much you can understand here. So angular position and linear position you are getting. Now next listen, secondary maxima. For secondary maxima, theta n equal to n plus half lambda by A, and linear position equal to capital D will be multiplied. And if you first secondary maxima you want to find, then n equal to 1 consider, second secondary maxima n equal to 2 consider, accordingly you get angular position or linear position. So for n equal to 1, first secondary maxima, my y1 is 3 by 2 lambda d by 2, for second secondary maxima it is 5 by 2 lambda d by A. Okay, so this way remember, and also remember width of central maxima is 2 times width of other maxima. So this one also remember, central maxima width always 2 times width of the other maxima. Okay, remember that. Now next is intensity distribution. So if intensity distribution you want to check in diffraction, y-axis take intensity, x-axis take theta. Now here you check here, this is your first minima. So how thing is coming, this is your central bright, this is your central maxima or central maximum, which is the intensity, or basically you can tell width is more than other maximas. Okay, other maximas. Did you understand clearly? Yes or no? So this is called intensity distribution in diffraction. So graph you to do graph. Okay, graph you to do. I hope everybody understands clearly. No worries. So this and this wave is which wave? Now this is your secondary maxima. Okay, like that you can identify which is what maxima. Yes or no? So now we'll do some numericals. Okay, theoretical we over. Now so we'll do some numericals.